And I'll start off sharing screen here and clean this up a little bit. So we were talking about performance optimization, and I went through the idea of caching components instead of accessing the transform translate, which means it has to go out and find the transform component. And instead, we cache a copy of it in a private variable, and then this is more efficient. And I demonstrated an example where we had a couple of programs talking to each other and doing get components in the update function. Get component is expensive, and instead we had the caching version where with a little bit of work we could make it more efficient, and I attempted to demonstrate that. Another optimization is to use the little square bracket arrays that are provided as part of Unity's C# implementation. These built-in arrays are very fast, mainly because they're a fixed size. You actually have to declare how big they are with a constant. You can't allocate them on the fly the same way you can with traditional arrays or lists that have other controls, things like add member and remove and sort and all the other things that you can do with a regular array. The built-in arrays are fixed size. They're very tightly packed so that they iterate easily. Because their linear layout in memory means that the cache handles them very well, your computer cache. So with the square bracket arrays, we declare them to be arrays with a little set of square brackets. When we want to use that array, we have to declare it to be a new vector with a constant in here or some assigned variable, but we have to declare explicitly how big it is. We can't add members at a later time. And then we can iterate through it with for loops, and it's very efficient. So a more complicated way to handle optimization is probably the best optimization, which is do less work. So for example, if you had an enemy AI that was out there doing stuff, one good idea would be to put the enemy AI to sleep or turn them off when the player was not in the vicinity of the AI. In that sense, we do nothing until the player is close enough for us to want to interact with them. Now, a slow way of doing this is in the AI's update function. We would test the distance between ourselves and the target presumably being the player. And if that distance is greater than 100, we bail out of the update function. We don't do anything in the update function. If it's close enough, then we go off and do some thinking and move the AI around and tack and do all the other stuff. But this is still expensive because each update function, it's doing this vector3 distance function, which is 3 multiplies, 2 adds, and a square root. As it finds the magnitude of that vector between the 2 points. So this is still work. It's better than nothing, but it's still work. So other solutions include things like using the on became visible and on became invisible functions that are built into the system. Another way is triggers, and the final and most efficient way is to use coroutines. So the on became visible and on became invisible are callback functions like on trigger and on collision that are, in this case, tied into the rendering system. As soon as any camera can see the object, on became visible will be called. So in our AI's code, we can have a simple on became visible function that enables the script that turns on the AI script. And when it becomes invisible, it's going to set enabled to be false and turn off the script. So we can control our AI or whatever it is with whether a camera can see it. Now, I'll warn you, this is any camera. So if you have an overhead camera in the scene that's looking down on the entire map, it sees all these things. And I believe actually, if you are running in the editor and you have the scene view open, if the scene view has a camera as well. And so I believe that on became visible will be true if the thing is visible in the scene view or in any camera in the game view. Also, with an AI, this would mean that all you'd have to do is turn your back on the AI and it would shut itself down. So that's not necessarily going to work that well. Another one is to use triggers. So if we have an AI that's patrolling in a particular area, we can turn it off unless the player enters a big box or sphere collider that's set to be is trigger, and we can test to see if the player has entered it, in which case we can enable our code. And if the player leaves the trigger, then we can turn it off. So triggers are another way of doing this. And you could actually put the trigger on the player so that when the player approached, the trigger would be this large collider around your player who that brought to life any AIs that you encountered. So that's another way to do it. Now, the final one is coroutines, and I've shown you coroutines a little bit, but I haven't talked about them very much. But coroutines are kind of where you write your own update function. The update function is the one that's called every frame, and in something like this where we're interested in the distance between our player and the target, our target, the player. In the update function, we're doing this vector magnitude, the 3 adds, 3 multiplies 2 adds, and a square root, and we're doing it every step of the update. But with coroutines, we can kind of take control of this. And in this example with the distance coroutine, I have as one of my exposed variables this public float wait, which is the time that I want to wait between doing the distance test. And so in the awake function or in the start, I do a start coroutine, my distance with that argument wait, and my distance is a special kind of function of type IEnumerator, and coroutines must be type IEnumerator. Now, in this case, I'm writing my own update function in a sense, and so I want this to continually loop, and so I use a while true. This is a loop that's going to continue forever, going around and around this while true loop. And in coroutines, I have access to the wait 4 seconds command, which is implemented with a yield return new wait 4 seconds, and then the argument wait how long I want it to wait. and then I do the distance. So what this means is that this is going to continually run, and it's going to wait for a certain number of seconds between tests of the distance between the player and its target, or the target and its or the object and its target. And I can show you an example of this here, where I have two little scripts on my player. I have the regular distance script that does it every update function, and I have this distance coroutine that in this case, the wait time is set to be 1 second. So this is updating its distance every second. So you can see right off the update function is, of course, doing it every frame, whereas the coroutine is only doing it every second. And I've got a little line drawn, debug line drawn between my player and the target that is keeping track of these things. Now, if you think about this, we're running at least 60 frames per second. So so I'm only doing 1/60th of the work with this coroutine that I'm doing with the update function. It's huge in terms of the amount of cycles that you're saving here. Now, you can of course adjust this. If our little AI needs to know more precisely how often it tests the distance to the player, then sure, you can set that time smaller and make everything work a little better. So that's one really important optimization, is kind of to take over the update function ourselves with a coroutine. Now, coroutines have other uses. Sometimes we might have a piece of code that has these different steps that are fairly expensive to operate. So in an update function, we might do step 1 or step 0 and then increment our state and then return. And then the next time through the update function, state is now 1. And so we'll do step 1, increment our state and return. And so we kind of break up the update function to do these different steps in order. And with coroutines, we can do this with a yield, return, new, wait for end of frame. So like the wait so many seconds, the wait for end of frame just waits until the next frame is available. So in this version of the update function, I would do step 0, wait for that frame to end, do step 1, wait for that frame to end, and so forth. So again, we kind of, if we have this kind of pathological setup where we have to do these different steps and they're fairly expensive, we can have these wait for end of frames to distribute the work out over a number of frames. The yield statement will delay execution until whatever the event is that we've specified here with our return new, in this case, the wait 4 seconds, 5 seconds, this is going to pause this part of the program for 5 seconds. I'm not exactly sure where the coroutines are run. I've seen some references that they run between the update and the late update function, but I'm not actually sure. You could check order of execution for that. So we can do some fairly fancy things with coroutines. Here's a little simple fragment of code where in the awake function, I spawn this test do function. And the test do function starts a coroutine do that has an argument 2. And in the IEnumerator do, it takes that argument, it prints that it's starting, it waits for that amount of time, and then it prints that it's finished. Now, if I run this, what I will see is that the start coroutine is not a blocking function. It will not wait until the do to is finished. It goes right ahead and prints the in awake after do. I believe it'll say the do starting first, since the start coroutine is before this debug. So it'll say do starting, then it'll immediately say in awake after do. And then after the coroutine is finished running, it'll say do finished. And I think I have this example here, and we can watch both the console where things happen and also the UI where I'm displaying things. So when I run this, it immediately says in awake after do. After 0 time, it says do starting. Oh, so it actually, no, it said do starting at time 0. It said awake after do also at time 0, no time at all between when it started the coroutine and when it went on to the next statement. And then here's the do finished after 2 seconds and some change. So the important thing here to recognize is that starting coroutines does not block on that statement. It continues on to the next statement while the IEnumerator is running. So this is running. Now, if I make a little change in this and I make the test do and a coroutine by making its type IEnumerator. This now means that I can do a yield return start coroutine do. Now, because this is a yield, this is going to block. So now that this is a coroutine and it has access to the yield statement, it's going to wait until the start coroutine do to is finished. So in this case, it's going to print do starting at presumably at time 0. It's going to print do finished at time 2. And then after this is completed, it'll do in awake after do. And so I have that version here, test do 2. And so watch over in the console and you'll see it shows do starting. 2 seconds later, it says do finished. And then after it has yielded that start coroutine, it does the in awake after do. So we can kind of chain these coroutines together. We can make these different coroutines block on a yield return blocks. So pretty much any event handler can be a coroutine. The void on trigger that we saw, you can just change that void to IEnumerator, and then the on trigger becomes a coroutine. And of course, you don't have to start it. It starts itself when the collider enters the trigger. You can't make update, any of the update functions a coroutine. So update, late update, and fixed update can't be coroutines themselves. They must be voids. But you can start coroutines in the update functions, and they won't block. They'll go right on to the next statement, and the coroutine will go off and do whatever timing it's done. And the other important thing is that any coroutine, any IEnumerator function that has multiple paths through its program, you know, if it has if, then, else kind of things, or while loops, or anything where there's branches in the code, every branch of the code, every possible path through the function has to have some kind of yield statement in it. So there are a number of different built-in yield instructions. There's the wait 4 seconds that we saw that takes as an argument the number of seconds that we want to wait. There's a wait 4 seconds real time, which is just a little bit different. It's actual wall clock time as opposed to internal unity time. This would be true if you had set the time scale to be something different and you were in slow-mo, but you wanted to wait for a certain number of real-time seconds. There's this wait for end of frame, which just waits, as it says, for end of frame. There's a wait for fixed update. And then there's some fancier wait untils and wait whiles, both of which require the use of delegates. I'll let you read about that in the documentation. If you want to end a coroutine, if you had that while true and it was looping around, but you wanted to stop it, you could have an if something yield break, and the yield break terminates the coroutine. And while it's not necessarily recommended, I'll note that yield return null is the same as yield return wait for end of frame. So a yield return null just waits for the next frame. As I mentioned, we've got this ability to wait. The wait 4 seconds can only be used with a yield statement. We've got wait for fixed update that waits for the next fixed update. These are some examples from the documentation. I've also got them here, but these are kind of the same as what I did with the do. In this case, I start a coroutine with a wait time of 2 seconds. Because the coroutine doesn't block, it immediately says before wait and print finishes, then wait and print waits a certain amount of time and prints, and you can play with that. I can make the start function and a coroutine by turning its type to IEnumerator. Now I have the ability to yield return the start coroutine wait and print. This will now block on this until the wait and print has finished. So it won't display this until after wait and print has finished, and then it'll display this. So this is kind of the same as those two do's. The important thing here is I'm showing you that the IEnumerator, that the start function, and I believe the awake function can both be set up as coroutines with yield statements. And remember, if it is an IEnumerator, it must have a yield statement for every path through it. So there are a couple of different flavors of the start coroutine. We can start a coroutine with the function, but there's also a string variety of this where we start coroutine with a string that has the method name. And in this case, we have a second argument, which is the value of the single argument that the method name defined by that string method has. This is one of the reasons for doing this is that it gives you access to the stop coroutine. I believe in Unity 2.19, they upgraded this so that we can stop coroutines other than with the string method, but the string method still exists. A drawback of this is that your method name, your function that you're calling with the string, can only have a single argument because there's only one slot for this. And apparently it also has higher overhead. So the way we would do something like this, we can start a coroutine, do something with an argument 2 seconds. We can then wait for a certain number of seconds, and then we can stop the coroutine. So the coroutine do something might have a while true loop in it that's continually going around and around and doing something. but we can explicitly stop that coroutine by calling its name. So the do something here is a while true. It's going around doing something, maybe making bombs or thinking about something, and it's doing a wait for end of frame or a wait for so many seconds, and it's going to be turned off by this stop coroutine that happens some number of seconds later here. I think I actually set up a couple of examples like this, where in the do something, I'm instantiating a little particle effect. And so I can show you that here. Start and stop with poofer. And so as this thing runs, it starts doing something with a 2-second interval between poofs, and you can see it doing something there, and then it reached the 10-second time limit, at which point I stopped it. To show you different variants, this one also works. I don't think this would have worked in Unity 217, but in 218 or 219 it did. So I'm starting coroutine in the more efficient way with the function name and its arguments, and I'm stopping the coroutine with the something name and its arguments. And it turns out that you must provide that argument there as well. There's other forms of doing this. You can make an IEnumerator variable and assign it to the name of the function with the argument that you want to pass to it. And then you can start the coroutine CO and do whatever you do, and then stop the coroutine CO. So we can kind of make a variable that contains the name of, that contains our callback, our call of the do something function. And finally, there's a coroutine CO that starts a coroutine do something interval, and we can stop it by stopping that coroutine CO. So 3 different variants here of how you can, actually 4 if you count the string method, ways that you can start coroutines and manage them. So that's all pretty cool. And these 3 versions of start and start with poofer are all exactly the same in their performance, but they each use these different methods. So I'm going to stop there and ask if there are any questions about coroutines. Coroutines are somewhat non-intuitive, but they are very, very powerful in terms of us taking control of the timing of different events. We're no longer dependent on the update function to execute what we want to do every frame. We can have these different yield statements, and it's a very powerful tool for taking command of timing. Any questions? Okay, well, I believe there's some readings and other examples about coroutines. So I want to go on to the next stuff that we're doing here. I want to start talking about making characters. And in particular, I want to talk about the character controller, which I alluded to back when we were doing physics. And I said, I showed you a little character and we tried to walk up a hill and some other stuff. But I didn't actually show you how to program a a character motor that will drive a character controller controlled character around our landscape. So if you remember back when we were playing with the horizontal and vertical axes, I made a little character that I could drive around the scene. I could drive this little character around the scene, and with the arrow keys, it would rotate and it would do all the stuff that it does. But I run into a problem with this kind of character when I put it on a terrain. So here now I have a terrain that my little character is playing on. And if I try and run this one, because I'm actually just controlling its position with the horizontal and vertical axes, it pays no attention to the terrain. It does not see it, even though it has a collider on it and all this other stuff. Because we're explicitly moving its transform around, it pays no attention to the terrain, and that's not a good thing. And this is how we did this with the Euler angles to rotate and to translate forward. So the character controller is part rigid body in that it does collide with things, and it's part rigid body in that it responds to the physics system. It's part collider in that it collides with things, but it itself is not controlled by the physics system. We control the character controller with two different functions, move and simple move, that we'll come to in a little bit. The character controller lets us do movement constrained by collisions, but we don't have to deal with the physics of a rigid body. Character controllers don't respond to forces, but they can exert forces, and they only move when we tell them to move. But they are constrained by collisions. They can't go through walls and they can't do other stuff. We saw the exposed variables of the character controller. So here's my little player that has a character controller on it. And we saw the exposed ones: the slope limit, the step offset, skin width, minimum move distance, the shape and size of this little controller. So, you know, we can change the size of the thing and make it fit our character in appropriate ways. But there are a number of hidden variables, hidden in the sense that they're only accessible from scripting. They're not exposed in the inspector of the character controller. One of these is grounded. So this is a little read-only variable of the character controller that tells us whether the character controller is touching the ground during the last move. We also have access to the character's velocity, how fast it's going. And we also have access to various collision flags that tell us what part of that capsule that is the character controller's collider has collided with something during the last move or simple move. And we can use this to, detect bullets that have hit us or things that have fallen on us from above and so forth. And there is a Boolean flag for whether we detect collisions or not. This is on by default, but we can turn it off. Now, the two functions that we use to drive our character around are the simple move and the move, or the move. We choose one or the other. The simple move moves the character with a particular speed. It's not really a speed, it's a velocity because it's a vector 3. But the simple move engages the character controller in the physics system in the sense that it ignores the y component of that vector speed that we're providing it with, and it replaces that with the physics engine gravity. Simple move returns a true false value that tells if the character was grounded. So the simple move provides us the same information that the is grounded provides us. Move is a little bit more complex because in this case, the move takes an absolute vector 3, x, y, and z, and there's no gravity applied to it. You have to handle the gravity yourself in the script. The move returns those collision flags that contain information about which part of the capsule is being touched. And the return values are none, sides, above, and below. So this tells us what part of the capsule is being touched. With the simple move, since we have no access to the y component of where we want to move our character, we can't make it jump. Whereas with the move, because we're handling the gravity ourselves, we can make it jump. And I'll show you examples of both of these. The character controller also sends messages with that on-controller collider hit that I showed you. This tells you the name of the collider that's hit our character controller when it makes one of these moves. So the simplest character controller here, simple move C, which is demonstrated below here. First of all, I want to point you to a directive that I've included here. We have the usual usings, but I've included in square brackets before the class definition the require component type of character controller. This is really cool because what this does is it means that I can't remove the character controller. If I try and remove it, it says can't remove the component because simple move script depends on it. The other thing that's kind of cool is if I'm in a scene and I've got a little character, let me make a little character here, a sphere that is going to be my character. And I'll just put the sphere over here and I will take that script, the simple move C script, and drop it on it and watch the inspector of that, which you notice has no character controller in it, but when I add that script, it automatically adds a character controller to it. So without doing anything other than adding the script, I've made my little sphere a player, and it's running a little slower than, and the camera's not looking at it, so it's not making sense. But that script directive is an important one and very powerful to, now I don't have to go through and say if I have a controller in my script, because I don't have to test for it because this has guaranteed that it's going to be there. As long as I'm here, let me show you the script that's on the camera that follows me around. And here I have another directive, which is the execute in edit mode. So this will execute not just when the game is playing, but when we're in the editor. And so if I haven't defined a target for my camera, that is, if not target is true, it goes out and finds a game object tagged player, If it finds such a target, it sets the target to be the game object's transform. That's what I need for that target. And in the late update here, if I have a target, it goes on and does this stuff. So that's another important directive, the execute in edit mode, that lets the script execute while we're in the editor. So back here with our simple controller, first of all, in the start function, I'm going to get component the character controller. I don't have to worry about it not being there because I've enforced that. Now, the rest of this is pretty much similar. I have a speed and rotate speed. I have this public bool grounded that I may or may not use. I have the public velocity vector. And these I'm not going to actually use, but I put them in the inspector so I could watch them if I wanted to. And the controller is private so that we don't see it in the inspector. Now, in the update function here, I'm going to access that controller is grounded, and I'm going to access that controller's .velocity. I'm not using them, but they will display in the inspector. I transformed the rotate with the horizontal axis, scaled by rotate speed and time delta time, rotating about the y-axis. I'm forming a float current speed that is my tuning parameter speed times the vertical axis, the up-down arrow keys that goes from plus or minus 1. And I do a simple move with the transform forward of my character. This is the unit vector that points out of the front of my character, and I'm scaling that by current speed. And so now my character very happily runs around the world, and you can watch grounded over here, and you can watch its velocity, and you can see its velocity going. And we very happily climb the hill here, and we can run down the ramp. And when I go off the ramp, you'll see that grounded turns disappears. And this is something we could use in scripting if we didn't want to be able to control it while it was in the air, which I can here. You could watch that is grounded and make it so you couldn't control the character when it's in the air. So that all works very well, and we now have a character that we can run around terrain, climb steps, do various stuff with a character controller controlled character. Now, the other version here, and again, I have a directive to require a character controller. I have speed, rotate speed, and I'm going to add a jump ability to this character, since with the move, I can access the Y component of that velocity. And I'm going to have a public gravity here as well, because I have to handle the gravity here. And I've got my move direction that I'll initialize to 0, and of course my character controller that I access in the awake function. This, by the way, is an example of caching, which we're doing so that we don't have to do get component in the update function. So this character I'm only going to allow to be controlled if it's grounded. So I'm going to test if the controller is grounded in the update function, and I'm not going to accept input from the get axes if I'm not grounded. So there's going to be no input to move direction if I'm in the air. If I am grounded, I'm going to rotate with the horizontal axes, and I'm going to again form a vector with the input get axis times our transform forward, our unit vector out the front of our player. I'm going to scale that by speed, and here's my test. If I do the jump button, jump is the space bar. If I do the get button jump, I'm going to replace my Y move direction with the jump speed. So I'm putting whatever that jump speed is here, 8 in the default, into my Y motion. I'm going to apply gravity. I'm doing this outside. This is grounded because, of course, I want it to apply gravity. And I'm going to subtract out the gravity time delta time. And then I'm going to, with that move direction, move the controller by this absolute vector. And I'm going to put a time delta time in here because I want it to move at a uniform rate, frame rate by frame rate. Now, there's a little puzzle here as to why we have gravity, why we have time delta time in here twice, because the gravity is in the Y component of my direction and of my move direction. And I'm using a time delta time here with the move direction as well. And this comes back to physics. If we integrate the F equals ma for a uniform gravity field, we get a parabola. Y as a function of time is its initial position plus its initial velocity times time plus 1/2 the acceleration of gravity times the time squared. And if I consider my little time step here, my little physics that I'm doing as an initial value problem, I should have the position updating with the velocity with 1 delta time and the acceleration with 2 delta times. I'm actually a little puzzled why the 1/2 isn't in there, but I tested this, and with the 1/2, it didn't behave the correct way. I put a little rigid body in here so that I could watch this thing fall. And if I watch this thing fall and step along as this thing falls, with the 1/2 in there, it doesn't fall fast enough. And so this is a puzzle that I have not actually solved, but the correct behavior for this thing is to have no 1/2 in there, even though the physics tells me that there should be. So now my little character runs around. Whenever it's not grounded, I cannot control it. So when I run off the ramp here, I can't control it while it's in the air. And actually, as we're running across this bumpy terrain, periodically I can't control it as it runs over the bumps and leaps into the air, and I can't control it when it's in the air. So that's our simple controller, simple move D. So the two different variants of this, the simple move that Unity handles the Y direction gravity for you, and the move where you have to handle the gravity yourself. The move where we have access to the ability to jump, the simple move where we don't, and a simple character with a motor. We sometimes call these scripts that drive our characters around motors because they are what motivate our character to move. So I'll stop sharing there and entertain any questions about the character controller. Monday, we'll start off with the mechanism system and start doing fancier characters with animations, and how we make motors for them and how we drive them around and synchronize their animations and do all of that stuff. We'll do that Monday. Any questions? Nice cat, Nick.
Thank you.
Thank you. you have any? Okay, we're all gone.